electrodes, and probably are the electrodes that are they are mostly used in the province and probably all over the world, that are 6010 and 7018, right? And we will go much in detail on this when we go through the consumables in the lectures, but they have their names 6010, 7018. Each number means something, and they're not random numbers, and if you know what they mean, you can easily trace what are they for, or what are the limitations of each electrode. But just to give you like a few main characteristics on each electrode, 6010 is when we are going through the name 6010, the first two digits are related with the tensile strength that the wall has. So this would be a number that here it's in KSI, but you can put it on megapascals if you want, but that's the tensile strength that your well will have, the minimum that is required by the code, the standard. And then the next digit, which is, sorry, I'm not presenting this. There you go. It looks much better. The next digit here, you will find that it's what are the positions you can weld with, right? One means all positions, and then you have different number for different positions or restrictions. And then the last number will give you a hint on what is the covering made of. 6010 is a high cellulosic, it's basically all cellulosic, all paper electrode. But if we go to 7018, which is, it has a little bit more strength, it can be used in all positions, but the 8 means that it has different other elements or compounds there, like limestone, potassium, iron powder, that they make. These are the elements that make the electrode easier to use. And if we look at the very end, we have also a code for when we have hydrogen requirements. So if we learn how to read these electrodes, which if you want to be in the welding field, you at least have to know. You don't have to like memorize by heart, probably, but for the quiz you need, but it's important for you to know that these numbers are not random, they mean something, right? So that's all for stick welding. I don't know if you guys have any questions before I start on SAVARC. So I would take that as a no. So SAVARC welding, this is also a process that it uses a consumable. In this case, it's as we can recall from the lectures, it's more closer to be like gas metal arc welding, because you have a wire that it's in a spool and it's being fed constantly, and the arc and the plate are you are producing an arc with an electrode that it's being fed by a spool. That's it. That's what it looks. That's the similarities with gas metal arc welding, but in this case we have no gas. Instead we have fluxes, so the weld will be covered in fluxes, and technically you don't need to protect your eyes, because it shouldn't be any arc exposed to your eyes, but still it's good to take all the PPE and precautions, because if the weld goes wrong, the arc might be there, and you might want to be protected anyways. So for this type of weld, for SAVARC welding, it's an automated process in terms of like it cannot be hand operated. Although I think we mentioned that back in the days, or in Russia, they tried to do it hand operated, but this process, you need from a power source, which in this case it's a Lincoln Power Wave AC/DC 100 SD, the one that you can see here in the pack with underneath the computer monitor, and you can see that all the system goes into these selection parameters here, where you can choose not only the voltage but the current of your process, right? So once you set current and voltage, the wire feed speed is going to be given by these two parameters. You also need something to move the torch, right? And this is why we have here an edge welding moving system, which is basically a system we use to move our torch on two axes, on Z axis and Y axis, so we can move it back and forward and up and down, and that let us make beats, straight beats, and then move our plate and do another beat next to it if we need to. Okay, and the hoppers that you see here, the black ones here and here with the Lincoln Electric and the CCWJ stickers are the ones that we use to put our powders. We will see now in much more detail. But about the electrodes, as you can see, you can see here that we have a contact tip. We have the wire here. In this case, it's a wire that it's a 1/8 inch thickness. It's a pretty big wire. The specifics of this wire we're using are here, but again, this is something we will go over when we see more in detail the consumables. But the interesting thing, or the thing that I want to point here, is that we have our contact tip or wire, and in this case it serves as the container for this hose that comes here that transport all the powders into the same container, right? And then we'll see how these two they merge and land into the plate, and I will show you now how it looks like. A little bit about the fluxes that we use. We have different kind of fluxes depending on the application and depending also on the wire that we're using. That they're depending on the wire, you should be using different type of fluxes. Again, you have the specifics of the fluxes that we use in these walls here, but just for you to have it, the chemical composition, what are the main compounds that you can find in a flux. And also I want to show you this because these fluxes, they come in this big bag and they're pretty expensive. And you might ask yourself, it's like, okay, I just like I made a run and then all the extra fluxes that we have that you'll see in action, is like, where do they go? You can reuse them, and this is how we reuse them in the lab. We just the slag that comes off and all the powders we just put in a colander and take off all the powder that still have some life into the hopper, so it can be reused again. This is, economically speaking, this is super important, because if not, you like the amount of fluxes that you will use in each wall that you can reuse, and it's big. It's a big amount of, it's a big proportion of fluxes that you reuse every well, right? You will see now in much more detail when we see the weld in action. So yeah, this is our short video of Savark. Let me try to play it without skipping anything. Okay, there you go. So the electrode, I didn't write it down there, but I'll show you which one we use, and you'll see now here, as you can see, before you start the wall, you just come close to the workpiece. You come close to the workpiece with your contact tip, and you let the flux submerge into the wire, and then you start the weld. One thing I like to mention here, and I would like to go back again, is like, although we say that this is a sub-arc process and we shouldn't be seen, or we shouldn't see the arc, and technically you don't need a welding helmet. It's good to be protected, or it's good to know that at some point the arc will be exposed. and you can see how the arc is exposed in this case actually. So that flashing that seems like nothing in the TV is something that you don't want to look at many times in a day. So it's important to keep the safety PPE with you, even though this arc is covered underneath all that flags. But you can see it's a long wall, and it's almost set on fire. All the flags is there. Once you finish the wall, you lift up the gun. Good question. Why does it explode at the beginning? I want to guess it's well. Thank you, Wesley. Yeah, it's a good it's a good practice to cut off the thin wire, and we do it every time, because as you can see, when you lift up the it's a good comment that Wesley did, is like when you lift up the wire, you'll see that your wire here has a lot of flaxes, right? So this is the part that you want before doing a follow another weld. You just want to cut off that part and start with brand new wire, if that's what you mean, Wesley. Sorry about that. I have troubles with the shortcuts with PowerPoint. All right. So once you finish the weld, you clean up all the extra flaxes that you have. As you can see, there is a lot of flaxes that haven't been used, and they can be reused. You just like collect them and put them back in the hopper again. But one nice thing to see here is like the slag, when it starts to cool down, the slag starts to automatically detach from the weld. That means that it's the weld was not too bad, at least. So you'll see how it looks like. This is on the right side, you have a weld without the slag, and on the left you have the slag and the weld. And you see how when you take it out, you see that slag, it's here, and you can see how it looks like. You can also crush these slags and reuse them, but that will depend on the type of wire you're using. So, but yeah, this is how a weld looks like, a sub-arc weld looks like. Oh, okay. Thank you, Wesley, again for all the interesting comments on all the processes. That's super good to have. So, any questions before we jump into gas metal arc welding? All right. Yeah, sorry, Jolene. I don't have an answer right now. I will look into and I will give you an answer, and then I will. No, I was gonna answer that, but then I start reading another few comments. But yes,
you mind if I just cover the explosion thing?
Please, Eddie, that would be awesome.
So if the wire has some coating on it that was due to melting or something, it has a lower, or it'll cause it won't contact as well as just a clean wire will. But also, if you're not traveling fast, like this wire is really big and it comes out fairly fast, so it'll push up, and then the powder that covers it doesn't cover it as well. So it's just a start. It's like a inconsistent stop start. But if it was traveling before you hit the button to start feeding the wire, it would be a smoother start. Thanks.
Thank you, Wesley.
One quick thing here. Start in all these semi-automatic processes, is very, very difficult. And much of the algorithms inside the Lincoln and Miller machines are about the start and the stop. What Wesley was saying is true. Like these electrodes, especially in subarc welding, they have an amount of silicon and manganese to deal with oxygen. When you stop the arc, that silicon reacts with the oxygen in the air and creates silicates. And the silicates is just ceramic, is silica, it's like a layer of glass. So when you put down the electrode to be in contact with the plate, many bad things happen. Number one, you don't conduct electricity through glass until you push it so much that you break the glass, and then the contact starts. And if you saw, not only there is an explosion, but the torch started to jump like crazy. That is because of the force of the wire pushing until it breaks the silicate. Then the arc starts, and then it fell, and it started to vibrate. In addition, we're gonna see this later, but when the wire is feeding, the wire has a temperature distribution that is more or less linear from room temperature at the contact tip to some other temperature very near the end, and then a very big spike that reaches melting towards the end. But when you are starting, all the wire is at room temperature. It's not having that temperature profile. So the start is a fairly traumatic event in welding. And in addition, we first started and then we did motion, but it's true what Wesley said too. If you start moving before you start feeding, when the electrode comes down and touches, then it rubs, and that will help. That's why also if you cut the wire, it helps. You do away with the silicate. If you ever pay attention to the welding machines, when they stop the arc, they have a whole algorithm that ends up giving you a relatively clean ball. But that's in MIG. In subarc welding, you cannot do that because you don't have shielding gas. Anyway, back to Ale. But we can talk about welding for the end of eternity, and it's amazing how much the laws of nature explain very practical things that have an impact on the bottom line.
All right, thank you, Wesley, and thank you, Dr. Mendes, for contributing to this, to answering the questions that I can answer. So, last process that I want to touch on and I want to go through is gas metal arc welding. And again, I want to go through how basic power source looks like and what are the main parts of the equipment. In this case, we know that we need the wire that is going to be feeding and it's going to be serving as the electrode of our arc process. So we need same as subarc, we need a wire spool, we need the drive rollers, and we need some system to drive or to feed the wire into our torch. So that's what we see here. This is the spool where all the wire is. As you can see here, size is much more smaller than subarc. Although they look similar, you see the contact tip here it's much more smaller than the one we saw before. And the gun in this case is for this machine we have a hand gun that we can use manually, so we can weld in our shop whatever we want in any direction, right? So the other thing that you might not see here is the gas inlet. This process needs gas. It can be argon, it can be CO2, it can be helium, but this process needs gas. So the machine, you will see that the machine it has a gas inlet as well, right? So this is a Miller MatE 212 auto set, and when it means auto set, it's like it's pretty easy to use if you're not into or you don't have many knowledge, because you can, with this equipment, it's designed to choose like only your wire size and then your plate size and all the parameters that like voltage or constant or wire feed speed. It will be given by those two parameters that you choose. So this is a pretty easy or beginner to start up with power source to use if you're not getting to MIG. Then For the experiments that I'll show you in a few slides, we use this machine, which is a much more sophisticated power source. It's a Lincoln power source. It's the power source itself it's the one that you see underneath the feeder. In this case, you have detached the feeder and the power source, one on top of the other. The feeders, you can see the same as the other one. You see the wire spool, you see the rollers, and then you see all through this. Let me see if I can grab the pointer. Through this line, the wire will go into the torch. In this case, the torch is it's an automated torch. It's placed in a system we can move back and forward, so we can do wells in just one direction, but with the steady this contact tip to work this distance, right? And the power source, it's a pretty sophisticated power source in which there are a lot of uploaded preset programs that you can choose depending. And again, if you can choose if you're welding certain type of material with certain gas, you can go and choose the program, and then the program will have already loaded all the parameters that you need. But also you can change them and customize all this program. This is a really state-of-the-art power source, and you can do many different things. So in this case, what we're gonna look at is like how changing the parameters, we can go through all these different transfer modes with just changing or the voltage or the wire field speed in this case, which will change the current. But by changing one of the and the other ones, we can go through short circuit to globular, and from globular to spray. And then we will see also and two other types of metal transfers that are, one is, I think we went through the different type of metal transfers in when we went through gas metal arc welding, and if you remember, we have what they call STT, surface, which is short for surface tension transfer, or pulse and pulse transfer, which are different transfer modes that they use the advantage of having new and state-of-the-art equipment that can play with the current or the voltage waves, just to have a different type of transfer mode. But we'll see now how they look like and how they sound. This next video has sound, so if you don't have your headphones or you want to turn on the volume, you will hear some bacon cooking basically. But yes, so let's go into the first transfer mode. So the first transfer mode is short circuit mode. We have everything, all the parameters here. There is not only one set of parameters that will give you this type of transfer. Of course, it's like the relationship between these two, and they will give you a different transfer mode. Of course, also it's very important to once you get the voltage and the wire feed speed, you need to readjust the travel speed, and also you need to be conscious that each transfer mode might need different type of gases, different type of mixtures. Some transfer mode they need more richer argon gases, and other transfer modes they can act just with CO2. For this case, for all the weldings that you will see now, that we try to fix all the parameters the same and just change the voltage and the wire feed speed. That's why they won't look or sound optimal. But just keep in mind that there are some transfer modes that can use some gases and other that they can't, right? So that's important to keep in mind as well. So basically, that's how short circuit transfer mode looks like. That's if we go back to the slide or to that graph where we have all the different transfer modes, we will see that it's on the very end of low voltage and low current, and it's basically when the wire hits the paddle, it creates a short circuit, and many times per second happens that, and that's what you hear, like the wire hitting the paddle and detaching, right? By the pinch effect. So this is good because you can weld in any position. Of course, this is an semi-automated process because we are welding with a system, but you can set up these parameters and weld with your hand. It has a low heat input, and the electrode efficiency is very high because you're literally like sticking the electrode into the paddle, right? The bad thing is like you can't weld thick plates. It's mostly used for thin sections, because if not, it can result in incomplete fusion or penetration. And sputter can be high. It's not the highest one, but sputter can be a problem in this type of metal transfer. So next one, I'm gonna go crazy with this. I'm so sorry about this going back and forward. Okay, we'll see short circuit one more time, and then we will see. Then we will jump into the STT mode. This is surface tension transfer mode. This is a Lincoln specific mode, but Miller has their own, Fronius has their own systems, and it's the one that we saw that has like this complex current wave, in which has a background current and a peak current, and they play with that to actually detach the molten metal from the wire. So in this case, the back current is it's around 60 amps, and the peak current it goes all up to like 300 amps. So that complex wave amp current wave that we saw on the lectures, those are the values, like peak and background values that we are managing in this case. Next one on our list is the spray transfer. This transfer mode, it requires high voltage and high currents, right? It's usually this one, for example, is usually used with richer gas and richer argon gases. Actually, 820, it's on the edge of like, you shouldn't be doing this with that much CO2. It's usually recommended argon to be higher than 85%, but just for the sake of showing you, this is how it looks like. And as you can see here, we increase the wire feed speed, we increase the voltage, but we also have to increase the travel speed, because we have a lot more of deposition, and you'll see how we have to travel faster. If not, it will be a mess. So you'll see that between the last two, the arc looks different, it sounds different, and if you can see, we can go back again, but we can see there is almost no sputter. Like you can see sputter going around, and again, this is another transfer mode that has a high efficiency electrode, because all the electrode it's spraying into the paddle, right? So next one, it's the pulse transfer mode, and in this case, again, the current it's gonna vary between being above the spray transfer like the necessary current to have a spray transfer mode, and then it's gonna go below, and that's what is gonna happen. It's gonna alternate up and down, and that's why it's called pulse. And you actually will hear this. Oh no, I shouldn't press space anymore. So you can see, sounds totally different. It's a really annoying noise when you're really close to the equipment. It can use higher amounts of CO2 compared to spray. It has a good penetration similar to spray, but again, same as STT, it needs power sources that are state of the art. They require like high tech, advanced power supplies. So that's one of the cons, that it's not, you can't do this with the make machine that you buy. I don't want to say Canadian Tire, but in any place, it needs specialized equipment to do this. We have one more. If I don't keep like skipping this, we have one more, which is globular transfer. And you can see a big difference between one and another. So basically, the advantages of globular transfer is that you can use, I think, correct me if I'm wrong, the ones that have more experience, I think you can use all CO2. You don't need to use argon in this case. Again, for this well, we didn't change the gas, but if you don't need argon, CO2 is much cheaper gas, and that's a big advantage in terms of efficiency. But it's restricted to certain positions. You can only do this in flat horizontal positions. You can't do this in any other position. And one of the bad things about this is also the sputter associated with the globular transfer mode. You can see that the well really looks bad, and surrounding the well there is a lot of sputter there. And even though you can reduce by adjusting some parameters, it's the transfer mode that has more sputter associated with. So yes, and if we want to switch from one transfer to another, it's again, it's matter of like changing in one direction with another. It's just or voltage or wire feed speed. For example, in this case, if we were in the very edge of changing from globular to spray transfer, because we were using high voltages and relatively high wire feed speed. So if we would have wanted to change into spray mode, we could have cranked the wire feed speed a little bit more, and you'll see how that changes in the way of in the transfer mode for the same parameters, except changing one or another. So that's everything I have for all these processes. Again, please ask me if you have any questions or any doubts, or you want to rewatch any part of the videos now. We can go through, or if you have no questions, thank you for everything. And yes, that's all that I have. I hope I can see you in the lab eventually, and we can try some wells, and you'll see how bad I am with the electrodes in my hands. But that's everything I have. All right, guys, have a good week and see you in 2 weeks from now. After the quiz, we're gonna do some more not experimental stuff. We're gonna do some calculations, but it's gonna be fun anyways.